Welcome back to the deep dive. Today we're taking on a really core topic in chemistry.
A big one.
Yeah, we're synthesizing the most crucial concepts from Chapter 7, which is all about redox reactions, reduction, and oxidation.
And our mission, really, is to pull out the key ideas from this, quite dense material and give you a really solid, structured review.
Right. We need to nail down the definitions, master how to calculate these things called oxidation numbers.
And then get to the ultimate skill, balancing those really tricky redox equations.
But before we get totally bogged down in all the rules and definitions, let's start with just a fantastic real-world application, photochromic lenses.
Oh, yeah. The ones in your glasses that go dark outside.
Exactly. Those glasses are basically a tiny reversible redox engine working on your face.
That's a great way to put it. The glass itself is infused with these tiny particles of silver chloride and copper I.
Chloride. And when UV light from the sun hits the lens.
That's the trigger. It kicks off an electron swap. The
Right.
silver ion, it gains an electron.
So it's reduced.
It's reduced, becoming a neutral silver atom. And for that electron to be available, the copper ion has to lose one.
Which is oxidation.
That's oxidation.
Yeah.
Here's a copper ion, and it's those new neutral silver atoms that start reflecting light, and that's what makes the lenses darken.
It's so clever, but then the reverse happens when you go back inside.
Exactly. No more UV light. So those copper ions that were just made, they're now able to pull the electron back from the silver atoms.
So they oxidize the silver.
They oxidize the silver back into transparent silver ions, and the whole process reverses. It's the perfect demonstration that oxidation and reduction are a team. They have to happen together,
One loses, one must gain.
always.
Okay, so let's unpack those foundational definitions from section 7.1. Historically, this all started with oxygen, didn't it?
It did. The original sort of classical definition was just about oxygen. Oxidation was gaining oxygen, reduction was losing it. Simple as that.
But that was a bit limited, I imagine.
Very limited. It led to the modern universal definition, which is all about electron transfer. And this is the one you absolutely have to lock in. It's the acronym OIL, RRIG.
Oxidation is loss of electrons.
Reduction is gain of electrons.
That applies to every single redox reaction, period.
And to really see it clearly, we break the reaction down into what we call half equations.
Right. So for something like sodium reacting with chlorine, the oxidation half would just be the sodium atom losing an electron.
Yep, Na becomes Na plus. And the reduction half shows the chlorine molecule gaining those electrons to become chloride ions.
Okay, that seems straightforward enough for simple ionic reactions, but the real skill is combining them, isn't it? Especially when the number of electrons doesn't match up.
That's the key. And there's one golden rule, it's non-negotiable.
Let me guess. The electrons have to balance.
The total number of electrons lost in oxidation must equal the total number gained in reduction.
Yeah.
To completely cancel out.
Okay, so let's use the example of nickel reacting with iron ions. Nickel loses 2 electrons, but the iron ion only gains 1 to become iron 2. So we have a 2 electron loss and a 1 electron gain. How do we fix that?
You just have to scale it up. You multiply the entire iron reduction half equation by 2.
So you need 2 iron ions to accept the 2 electrons from that 1 nickel atom.
Exactly. Then the 2 electrons on each side cancel out, and you get your balanced overall ionic equation.
I remember another example from the text that was a bit more complex with iodide ions and manganate.
Oh, yeah, that one.
The iodide loses, what, 2 electrons, but the manganate gains 5,
Right, a 2 and a 5. So you have to find the least common multiple,
which is 10.
10. So you multiply the iodide half equation by 5, and you multiply the manganate half equation by 2. It gets a little more messy with the algebra, but the principle is identical. Balance the electrons first.
So we've covered electron transfer for ions, but what about, and this is where I think it gets really interesting, covalent compounds? There's no obvious, total transfer of an electron there.
And that is exactly why we need the concept of the oxidation number, or ON.
The ON.
Think of it as a bookkeeping tool. It's a kind of imaginary charge we assign to an atom in a molecule that tells us its degree of oxidation. The higher the positive number, the more oxidized it is.
And it's crucial that it refers to just a single atom, right? Not the whole molecule.
A single atom, yes.
That sacrificial protection example is really helpful here. You bolt a block of magnesium to a ship's hull. The magnesium starts at an ON of 0.
Right, because it's an element.
And it gets sacrificed, it gives up its electrons to protect the iron, and its ON shoots up to +2. It's a perfect visual for that increase.
And to calculate the ON for any atom, We just have to follow 6 essential rules. There's a clear hierarchy.
Okay, let's go through them. Rule 1.
Any uncombined element is 0. Zinc, metal, chlorine gas, whatever, ON is 0. Monatomic ions. The ON is just the charge. A calcium ion, Sec2 plus MAV, has an ON of +2.
Simple.
Rule 3 is about elements with fixed values. Group 1 metals are always +1. Group 2, always +2. Fluorine is always -1.
Hold on, let's pause there on the most common ones. Hydrogen and oxygen. Are they always fixed?
Great question. They are almost always fixed, but they have important exceptions. Hydrogen is almost always +1. Unless it's in a metal hydride, like sodium hydride, then it's forced to be -1. And oxygen is your go-to -2.
But I definitely remember exceptions for oxygen. What about in hydrogen peroxide?
That's the one you have to know. In peroxides, oxygen is bonded to another oxygen, so its ON is only -1. And in a very rare case, if it bonds with fluorine, the king of electronegativity,
Fluorine wins
and forces oxygen to have a positive ON of +2. You just have to learn those exceptions.
Okay, so rules 4 and 5 are the big calculation rules.
They are. Rule 4, the sum of all the ONs in a neutral compound adds up to 0.
And rule 5, the sum of all ONs in an ion equals the charge of that ion.
Yes.
Let's test them. Sulfur dioxide, SO2. It's neutral, so the total has to be 0. We know oxygen is -2, and there are 2 of them.
So oxygen's total contribution is -4.
Which means sulfur must be +4 to make it all balance out to 0.
Simple as that. The rules give you the answer.
Now for an ion, the nitrate ion, NO3. Rule 5 applies. The total ON must add up to -1.
And the 3 oxygen atoms contribute a total of -6.
So nitrogen's ON plus -6 has to equal -1.
Which means nitrogen must be +5.
Right. And these rules let us find that number for any atom, whether the bonding is ionic or covalent. It just works.
And that brings us to the most powerful definition of all. Oxidation is simply an increase in oxidation number.
And reduction is a decrease in oxidation number.
That's it. So much clearer.
It also makes defining the agents much easier. Let's take the oxidizing agent. It's the substance that causes oxidation. So what happens to the agent itself?
Well, to cause oxidation, it has to take electrons from something else, so it is gaining electrons.
Meaning its own oxidation number goes down, it gets reduced.
Exactly. The manganate ion is a classic, powerful oxidizing agent. In the reaction, the manganese atom's ON plummets from +7 all the way down to +2.
And the opposite is true for a reducing agent. It causes reduction by donating electrons, so its own oxidation number goes up. It gets oxidized.
Like the iron ion changing from +2 to +3. A classic reducing agent.
Understanding this is so important because it leads us to, I think, the pinnacle of this chapter, balancing those really complex equations using the oxidation number method.
This is the high-level skill.
Okay, let's slow down and walk through the 4 steps. 1, identify the ON changes. 2, balance those changes with coefficients. 3, balance the overall charge using H+ ions. And 4, balance everything else with water.
Let's do it with that classic reaction, manganate ion with the iron ion in acid.
Okay, step 1. We already said manganese goes from +7 to +2.
That's a change of -5. Reduction.
And iron goes from +2 to +3.
A change of +1. Oxidation.
Step 2. Balance the changes. We have a -5 change and a +1 change to make them equal.
We need 5 of the +1 changes. So we need 5 iron ions for every 1 manganate ion. That locks in our main coefficients.
1 manganate, 5 iron, 2 ions. Got it. Now step 3, balance the charge. Let's look at the left side, the reactants. The manganate is 1-. The 5 iron 2 ions are a total of 10+.
So 10+ and 1- gives a total charge of 9+ on the left side.
Okay. Now the products on the right. The manganese 2 ion is 2+, and the 5 iron 3 ions are 15+.
2+ and 15+ is 17+.
So we have 9+ on the left and 17+ on the right. We need to balance that.
And we do it by adding H+ ions to the side with the lower positive charge. We need to add 8 H+ ions to the left side.
So 9+ plus another 8+ from the hydrogens gives 17+. Now the charge is balanced. Final step, step 4. Balance the atoms. We just added 8 hydrogens to the left.
Which means we must add 4 water molecules, 4 H2O, to the right side to balance them out.
And those 4 water molecules also perfectly balance the 4 oxygen atoms from the original manganate ion.
And there you have it, the final perfectly balanced equation. It's the gold standard method.
It's so important to remember this isn't just for balancing. The whole ON concept is built into systematic naming. That's section 7.6. we use Roman numerals.
Absolutely essential. You
Yeah.
can't just say iron chloride.
Because it could be +2 or +3.
Right. We have to say iron 2 chloride or iron fluoride. The Roman numeral tells you the ON. It tells you exactly which compound you have.
And that applies to nonmetals too. Something like sodium nitrate. That V tells you the nitrogen atom in there has an ON of +5.
Which allows us to do the reverse from section 7.7, work out the formula from the name.
Okay, let's try it. Sodium chlorate V. We know sodium is +1. The name tells us chlorine is +5.
And the whole compound is neutral. So the chloride ion part must have a charge of -1 to balance the sodium.
Right. We know oxygen is -2. So we just need to solve for how many oxygens there are. Let's call it N.
So +5 from the chlorine plus N times -2 from the oxygen must equal -1.
5 minus 2, N equals -1. So 2N must equal 6. N is 3. The formula is NaClO3.
Exactly. The ON is the key that unlocks a formula.
Yeah, sure. Finally, let's touch on a really specialized, kind of weird reaction type from section 7.9. Disproportionation.
It's a great word. It's basically a self-reduction oxidation.
Meaning one single element is both oxidized and reduced in the same reaction.
It splits its personality, chemically speaking.
The classic example is chlorine gas reacting with cold alkali. Chlorine starts at ON0, and in the reaction, some of the chlorine atoms get reduced to chloride ions with an ON of -1.
And at the same time, other chlorine atoms get oxidized to the hypochlorite ion, where chlorine has an ON of +1.
It goes from 0 both down to -1 and up to +1.
And because the change is equal in size, a drop of 1 and a jump of 1, the products are formed in a 1-to-1 ratio.
But the text contrasts that with what happens if you use hot, concentrated alkali.
Yes. The conditions change everything.
The chlorine is still reduced to -1, but this time it's oxidized way further, all the way up to the chlorate V ion.
So its ON goes to +5.
Now you have a change of -1 and a change of +5. The balance is completely different.
Totally different. To balance the electrons, you now need 5 atoms to be reduced for every one that gets oxidized to that +5 state. It completely changes the stoichiometry of the reaction.
Wow. So that was a full journey through redox chemistry. Let's just quickly recap the 3 big pillars from today.
First, at its heart, redox is about electron transfer. Just remember oil rig, and we use that to build half equations.
Second, oxidation numbers. That's the key accounting tool that lets us track oxidation in any compound, ionic or covalent, by following those 6 rules.
And third, we use those ONS for systematic naming and, most importantly, to power through that 4-step method for balancing even the toughest equations.
Right, and we talked a lot about defining oxidizing and reducing agents, but we never really touched on how strong they are. The text mentions standard electrode potential.
Yes.
I think the provocative thought for you to take away is this. Everything we learned today is the map you need to understand how that electrode potential number relates to the actual power of a substance. How good is it at being an oxidizing or reducing agent?
That's the next level. That's where this knowledge truly comes to life.
Thank you for being a part of our little last-minute lecture family.